Hello, sir. This is Meer Shah, and this is my presentation on the study Fracture Strength by Torsion Test at the Implant Abutment Interface. Firstly, I'd like to start off with a few pictures of what a normal tooth looks like and what fractured teeth look like and what an implant abutment interface looks like. And as we can see in the interface, there's a crown, there's an abutment, screw, and the implant. So how does a fracture occur? Fracture can occur due to bending moments, uh, excessive axial forces, horizontal loading, and rotational torque such as jowing, grinding, and clenching. In this study, we're going to look at rotational torque. This is some background information. Um, Here's how an interface looks like with a screw, an abutment, and an implant body embedded inside the gum of a person's jaw. The purpose of this study was to investigate fracture strength using a torsion test at the implant interface in order to assess the effect of torsion force on the connection. This was achieved by measuring fracture torque and torsional yield strength. Currently, there are hundreds of implant systems and tests available on this topic, but none or very few give the exact data on the abutment connection design implications. Here is a brief description on the method. So they took 30 screw implants of diameters 3.3, 3.8, 4.3, 5.0, and 6.0 millimeters, 6 screws of each diameter. This is a mere representation of different sized diameters. The implants were connected to abutments with screws tightened to a torque of 20 Newton meter using a digital torque meter. Mechanical stress was applied with a rotational speed of 3.6 degrees per minute until it fractured. Fracture torque and yield strength were measured compared using Tukey's test. The implant abutment interface were examined using a scanning electron microscope (SEM). This is a picture of how an SEM looks like. Results. Okay, as we can see, this figure shows the relationship between torsion angle and torque. It shows that the fracture occurrence from the torsional load follows a parabolic curve, as we can see. Initially, for all the diameters, as the angle increases, the, the torque increases proportionally. When the line starts to curve after the phase, it's referred to as yield point. It occurs after plastic deformation. With a further increase in angle, the interface reaches breaking point here, or as we can call a fracture. The graph on top shows the mean value of maximum fracture torque strength. The mean maximum fracture torque were quite similar for diameters 3.3, 3.8, and 4.3. On the other hand, the mean maximum fracture torque for 5 and 6 millimeters were quite high, as we can see. The graph below shows us the mean torsional strength, which was significantly different for all the diameters. Next, moving on to the scanning electron microscope picture. In this image, we can see that all the implant abutment connections, they had been damaged, all of them. Internal notches of the implant body remained intact, but all the projections of the abutment had been fractured. As we can see covered in this red circle, in all of the diameters, the abutment was fractured. Moving on to the discussion, uh, the relationship between static torsional load and the fracture occurrence is followed by a parabolic curve as we saw before. Smaller diameter implants fractured much easier and earlier at the implant interface. The scanning electron microscope images showed that although the anti-rotational notches had been destroyed, the corresponding internal grooves remained intact. The paper also gave information about other studies which are related to this study. Firstly, by Nagel, this studied the implant abutment connections of each replace, select, and the camlog implants. Replace select implant may fail by fracture of implant body at the thinnest part of the wall. Another study was by Huang HM. This test reported a similar load displacement curve as this study. Another test was by Balfour and O'Brien. Balfour and O'Brien tested three kinds of implants for maximum anti-rotational stability. The three kinds were, one of them was external hexagon type 0.7 mm diameter, internal octagon type 0.6 mm diameter, and internal hexagon type 1.7 mm diameter. They fixed a calibrated torque gauge to the abutment sleeve and applied torque until all of them fractured. In the internal octagon and internal hexagon designs, failure was limited to the abutment connections. Balfour and O'Brien result differed from this study, although the results from this study confirmed the torsional strengths were different depending on the connection dimensions as reported by the Balfour and O'Brien study. Another study in this paper shows a comparison between mechanical strength of CPTI screw implants. There are of two types, internal tube-in-tube, as we can see in the picture on the left, and external hexagonal type, as we can see in the picture on the right. Different torsion forces were applied to both. The hexagonal type were heavily damaged in all the phases of loading. Deformation occurred in both the implants as shown in figure 6. Figure 6 is the SEM shown on the right. Also, deformation occurred immediately before torsion fracture in all the specimens. Lastly, we move on to conclusion. So, what determines mechanical integrity of an interface? There are many factors including screw preload, abutment connection design, fitness of components, loading conditions, and torsional forces. Forces that led to permanent deformation were dependent on the diameter of the implant. Implants with a higher diameter achieved higher torsional strength as compared to lower diameter implants. This is because of the size and thickness of the implant walls. Furthermore, anti-rotational notches were destroyed only in the camlog implants. This is due to differences in strength and tensile properties of the materials. Finally, how can we say that this study was reliable? Firstly, they used a variety of diameters. Secondly, all the implants were of the same material, which is titanium. All the screws were tightened to the same stress, to the same torque, 20 Newton centimeter. They all underwent the same rotational speed, 3.6 degrees per minute. And finally, they compared their results to those of other studies for better calibration. Thank you.